All right, let's begin by talking about electric fields. Electric fields are a way to understand how charged particles interact with one another. So imagine that we have a charged particle here, positive charge in this case. The electric field is something that surrounds the particle in all regions, and it extends infinitely far into space. And if another charged particle comes by, it has its own field, and those two fields interact with each other. And that's how the particles interact, is through their fields actually interacting. The basic idea is that the field goes off into space in all directions, goes infinitely far. However, it's not the same magnitude at all distances. So in that sense, it's like a vector. So these are often called vector fields because they have a magnitude and they have a direction associated with them, just like a regular vector. For a positively charged particle, if you have a charged particle like this, it's isolated by itself. You can think of the electric fields as going radially outwards in all directions from the electric fields. Now, just because I've drawn it symmetrical here, I suppose in the case of a single point charge, it would be symmetrical, but just because I've drawn the field lines at 90 and 45 degree angles doesn't mean anything. It's just easy to draw that way. You could have multiple lines going off in any direction. But notice the field lines are close together here whenever you're near the particle. And the field lines get farther away when you get farther away from the particle. Now, that has to do with the magnitude of the electric field. So we would say the magnitude of the electric field is stronger here because the field lines are closer together. And that would be true no matter how many field lines you draw. They're going to be closer together when you're near the particle. They're going to be farther apart, and therefore the electric field is weaker the farther away you get. Okay? So for a positive point charge, the electric field lines point radially away in all directions. And this would be spherical, three-dimensional, if we could draw it that way. Now, if you had an isolated negative charge, the field lines also are drawn the same way. Again, just because I'm drawing it at 45s and 90s doesn't mean anything. But the direction of the field lines are going to be the opposite direction for a negative charge. So they're going to have directions that point towards the charge, point inwards like that. Okay? So the electric field lines radiate outward away from the positive point charge. The electric field lines radiate inward from the negative point charge. Now, I said these electric field lines are vectors, and they are. And we've drawn them as nice straight lines, but that's not always the case. You could have electric field lines that do things like this, okay, and have some direction associated with them, which we indicate here with the little arrowheads, just like you would a vector. But if you wanted to know what is the magnitude of the electric field at, say, a point, let's say, what is the magnitude of the electric field at that point right there? Well, you would have to have a formula or an equation or some mechanism in order to compute the magnitude of the electric field at that point. But the direction of the electric field at that point is always going to be a tangent to that curve, whatever that curve happens to be. So that would be the direction of the magnetic field at that point. Because the lines are curving, you pick a point, draw a tangent line to the curve, and that's the direction of the electric field at that point. Okay. Well, you could also have electric fields that are not just due to point charges, but to continuous charge distributions. Let's say, for example, we have a line, and that line has positive charge distributed all along it. So this would be like a continuous charge distribution of positive charge in some linear charge density. Some lambda exists for this. Okay. Well, those positive charges, you can think of those if you get closer and closer and closer to it as individual charges, and they're going to have electric field lines that radiate outward in all directions as well. Okay? But next door to that charge, there's another charge, and its electric field lines do the same sort of thing. Like that. Well, if you think of that as continuous charge distribution, but you're dividing it up into little differential charge segments, then for every one of these charges that goes, say, in that direction, there's another component down here that goes in the opposite direction. And those two things would cancel each other out. And the same would be true for these parts here, and these parts here, these parts here, these parts here. So what's happening is the horizontal components are canceling each other out, but these components that I've drawn as vertical lines pointing radially away are still there. Now, this is a line of charge. It's not just a line on a piece of paper. It has some dimensionality to it. So you would also end up with electric field lines going out this way, going out that way, going this way, and going that way, and that way. But the lines are going to always radiate away from the charge. So imagine that you've got a string here, and the lines are coming straight out off of the string. None of them are at an angle relative to the string other than 90 degrees away from the string. So that would be an example of a linear charge density in the electric field. Now that would be true for all the points except down here at the ends. At the ends, you're not going to have these components canceling. So at the ends, you're going to experience something called fringing. And that may be easier to see if you imagine like a sheet of charge. Let's say that we've got a flat surface here. Here's something. This is just a flat surface. And we place some charge on that flat surface right there. Okay? And let's look at it from the side. So we're looking at it edge on like that. And there it is right there. And let's say we've put some positive charge here on this face of it. All right, so the positive charge is just sitting there. Well, like we had in this case up here, but remember there's some dimension to this, so we're actually looking at it edge on, so it goes into the sheet of paper here. But those electric field lines are going to behave the same way up here. And what's going to happen, and the net effect is that the electric field points radially away like that until you get here on the end, and then it's going to start doing things like this. Okay? Like that. So that's fringing. So if you wanted to have nice, what's called a uniform, and in this case it would be constant. So a uniform, constant electric field, then you would stick close to the center of this conductor, and or center of this surface here, in this region right here, and you wouldn't want to get close to the edges, because when you get close to the edges, you get fringing like that. So this is this would be a way to represent a uniform electric field. Okay, these parallel lines spaced like that represent uniformity. So if I have let's say over here, I draw another plate like that one, and then let's put another plate underneath it here. On the top plate, we'll put positive charges. On the bottom plate, we'll put negative charges. And there's just as much positive as there is negative. The electric field lines are always going to point like this. They radiate away from the positive charges, and they terminate on the negative charges, like that. Except when you get too close to the edge, and then they're going to do things like this. So you get fringing out here close to the edges, like that. Okay, and once again, this is a way to make a uniform electric field. And what I mean by constant in this case is the electric field value, say at that point right there, is exactly the same at that point right there, and it's exactly the same at that point right there. So the magnitude of the electric field and the direction of the electric field at all of those points, in fact, any point in this region here in the central part, is the same. So that's what I mean. It's uniform. You can tell that from the parallel lines, and it's constant, because it has the same magnitude as well. Well, you can have electric fields in other sorts of charge configurations. Let's say that we take a positive charge, something like a proton, some small positive charge, and we put a small negative charge right next to it. Now, these would be really close to each other on the order of nanometers, let's say. The electric field lines start at the positive charge, terminate at the negative charge. But they don't just go in a straight line like that. They're going to go like this. And you may have seen this kind of pattern, and you very likely will see this kind of pattern if you do a lab exercise where you have to map the electric fields. Something like that. And then radiating away that way and coming in that way. So all these electric field lines have directions that go from the positive charge to the negative charge like that. This is an example of a dipole. And there are lots of molecules in chemistry that you will encounter that can be modeled as if they are dipoles like this. An example would be a water molecule. A water molecule is H2O. Water molecule is H2O, and if you were to sketch that out, you've got, here's your oxygen, and your two H's are up here, so it looks kind of like Mickey Mouse, so it's called the Mickey Mouse molecule. But that's water right there. And you'll notice there's more up at one end than there is at the other end, which lends itself to be modeled like this. So a water molecule is a dipolar type of molecule. All right, let's say we've talked about electric fields. We've given some examples how to sketch them and so forth. We've called this a vector field, and it is. And we're going to use the symbol E for the electric field, but it is a vector, so we'll put that little arrow over the top of it like that. Now, because it's a vector, you know it's going to have a magnitude and a direction. The direction we have kind of already talked about, how the positive charges are emitting the electric field lines and the negative charges are receiving, or the electric field lines terminate at the negative charges. So that's the direction right there. That's how you're going to figure out the direction. Magnitude, though, comes about because of the definition of what electric field is. And here's the definition of electric field. Electric field is equal to the amount of force per charge here. And if you look at that, you can tell what the unit of electric field is going to be. That's a Newton on top and a Coulomb on bottom. So a Newton per Coulomb is a unit of electric field. Okay, but this idea here, this is the definition of what electric field is. So what does that mean? That means that if you have an electric field, let's say we've got an electric field, this would be a uniform electric field, and I take and put a point charge right there. That point charge is Q naught. Okay, that point charge is Q naught. That point charge is called a test charge. That's why it's got that little subscript 0 on it, because it's meant to be a small number, a small charge, small quantity of charge. You want it to be small because you're going to use that to test what's going on in this electric field that's external to the charge. So really, the reason you want it to be small is you want it to be so small that its own electric field does not affect the surrounding electric field. So you're using this charge to test the electric field. So you put the charge there, you measure using some mechanism what the force is on that charge. And then you take that force that this charge experiences, you divide it by the charge itself, and that's the electric field. Notice, force is a vector, so the electric field points in the direction of the force. And that is true unless this charge happens to be negative, in which case it's going to point in the opposite direction. Okay? All right, so that's the definition of what electric field is. It's easy to use this definition then to compute the electric field for a point charge. So let's say we've got a point charge here. There's our point charge. It has some charge value of Q. And nearby, let's say right here, that's where we're going to put our test charge. Well, this positive charge, you know, the electric field lines go off in all directions, like that. And this point charge is a distance away. Let's say that that distance right there is R. All right, so we can figure out what the force is going to be on our Q naught charge just by using Coulomb's law. The force is going to be K, Q, that's this Q, times Q naught, that's this Q, divided by the distance between the 2 point charges squared. So there's the force equation. The electric field then is defined as F divided by Q naught. So if I take F, that's K, Q, Q naught, divided by R squared, and then I put a Q naught on bottom, notice that the Q naughts cancel. So the value of Q naught doesn't even really play a role here in the electric field. The electric field for a point charge is then K, Q over R squared. Now, notice something about this equation. First of all, it's just got Q in it, and Q is the charge that is generating the electric field. Has nothing to do with this charge here. So that charge might as well not even be there. If we're out a distance R away, and there's just a point in space, there's no charge there, that's just a point in space right there, then the value of the electric field at that point is given to you by this equation. So you could figure out the electric field value anywhere surrounding a point charge with this equation. And then the direction of the electric field is going to be given based upon what big Q is. Is it radially away or is it toward? If it were a negative charge, this Q would be negative and your E value would also be negative. Okay, so it's pointing inward. So a positive electric field means that the electric field lines are pointing outward. A negative electric field would mean that the field lines are pointing, the field lines are pointing inward. So let's work a very brief example then. Let's say that we've got let's pick a proton. Okay, and we want to know what is the magnitude of the electric field. So what is magnitude and direction of the electric field at 1 centimeter from the proton? That's pretty straightforward. You've got some positive charge here. Your distance R is going to be 1 centimeter, and there's the place 1 centimeter away where you want to know what the electric field is. Okay, we can use our electric field equation. That's just going to be K, Q over R squared. Let's plug in our values. 9 times 10 to the 9th Newton meter squared per Coulomb squared times Q. Okay, what's Q for a proton? You should know that. If I were you, I would commit that to memory. You're going to use it so often. It's 1.6 times 10 to the minus 19 coulombs divided by the distance, which is just 1 centimeter, so that's 10 to the negative 2 meters, and then square it. Now, do that multiplication real fast. I end up with 1.44 times 10 to the negative 5th newtons per coulomb. Okay, that's the magnitude of E. But remember, E is a vector. What direction is the electric field going to be at that point? Well, it's a positive charge, so it's going to be pushing, as we've got it drawn here, and it would be to the right. But, you know, there's nothing that says the point is to the right of the proton, so you need to be aware of that. So how do you express direction here? The easiest way to express direction is to say this. It is radially outward. from the point charge. So that's probably the easiest way to say that. Then, if you're working a problem, draw a box around it, there's your final answer. Okay. Let's look at something else then. Let's say that I have some point charges that are along a line here. Here's my line, here's my point charge, here's my other point charge. Just for the sake of argument, let's say they're positive. So those are both positive point charges. Let's say this one is Q1, and this one over here is Q2, but Q2 has a value that is 1/4 Q1. Okay? The distance between these two charges, we're going to give it a variable named L. Okay, now I want you to think about what's going on here. These are going to have electric fields that go outwards in all direction. This one as well, outwards in all direction. And I want to know where is E equal to 0. So where is the net electric field 0? If you'll think about it, up here, let's say up here, the electric field line, for example, from this charge is going to go that way. The electric field line from this charge is going to go that way. There's no way that those two field lines could cancel each other. In order for them to cancel each other, they have to be in opposite directions. And if you go through that kind of analysis in all directions out here, and if we did it over here, you got that one coming from Q1, that one coming from Q2 maybe. There's no way for those to ever cancel each other. But where are they going to be able to cancel each other? Could it happen over here along this line? Could it happen over here along the line? Could it happen in the middle along the line? Well, if you think, along that line is really the only place that it could ever possibly cancel. So if E1, that's the electric field from charge 1, points that way over here, the electric field from charge 2 is also going to point that way. So those can't possibly cancel because they're not in opposite directions. Same's going to be true out here. E1 is going to point that way and E2 is going to point that way. But somewhere along the middle here, E1 is pointing that way every place along the line. E2 is pointing in the opposite direction, like that. So those could potentially cancel if their magnitudes are equal. So once again, there's no possibility of canceling anywhere out here to the left of Q1. There's no possibility of them canceling to the right of Q2. There's no possibility of them canceling above or below the line. So really the only place that they can truly cancel is going to be along the line between the two charges. But only at the spot, only at the point where the magnitude of E1 equals the magnitude of E2. All right? So where is that? Where is E equal to 0? All right? Well, let's pick a point. Let's say that point right there. Now we know the total distance is L. Let's call the distance here X. And X is going to range between 0 and L here. Then the distance over here to Q2, that's going to be L minus X. Okay, so what we want is we want to know where is the magnitude of E1 equal to the magnitude of E2. Where does that happen? Okay, well the equation for E1 is going to be K Q1 over X squared. That's the magnitude of the electric field at our point X. And X can be any value, but we're just choosing to call it X, the variable X, but it could be anywhere along here. So that's the electric field at that point. That's the electric field due to Q1. Then the electric field due to Q2 is going to be K Q2, but instead of writing Q2, let's just write 1/4 Q1 divided by the distance that point is away from Q2. And that distance is L minus X squared. Okay, now we're looking at the value of x where e is equal to 0. We're looking for that. So you can see that some things are going to cancel. The k's cancel. The q1s cancel. And what am I left with here? I'm left with 1 over x squared on the left-hand side, and I'm left with 1 over 4 L minus x quantity squared on the right-hand side. Okay, let's take the reciprocal of both sides then. We've just got x squared equals 4 L minus x squared, like that. Okay, now to get to a solution, there's a lot of ways to do this. It's a quadratic equation, to be honest, but we could take a square root right away. We know that x is going to be positive because we're measuring it from q1. So we'll just take the positive roots. This is just x. Take the square root of the right-hand side. Square root of 4 is 2. Square root of that in parentheses is just L minus x. Okay, let's distribute the right-hand side. 2L minus 2x equals x. Now I'm going to move over here and start solving that. Let's take the x that's on the left-hand side. No, let's take the x that's on the right-hand side and put it on the left-hand side. And now we've got 3x equals 2L, like that. So solving for x is going to be 2/3 of whatever L is. So there's our answer. That's where e is equal to 0. So it's 2/3 of the distance between the two to the right of Q1 as drawn. So there's our actual entire answer. We need this part down here. Otherwise, this is just a meaningless quantity. All right, so we have worked a problem where we figured out where the electric field along this line is 0, and it turns out that it's going to be 2/3 of the length away from wherever Q1 is.